Hello, this is my video report for Lab 4. So the purpose of this lab is to observe and measure the distance dependence of bar magnets and their magnetic field, and how those magnetic fields change as distance changes, and compare those measurements to the predictions that we made deriving from the Biot-Savart law. And from our results, we found that n is equal to negative 2.8262 and mu is equal to 7.4. So some fundamental principles that we are using here, we're using the Biot-Savart law, which describes the magnetic field generated by a constant electric current, and then the magnetic field model of a dipole that is used at any location, and then the distance dependence formula of a bar magnet, which we then linearized using Ln. Now for the observed model, we have the initial conditions with the bar magnet and the magnetometer app on the phone, and then at the system we have the bar magnet, and then the surroundings being everything else. So using the Excel sheet, we measured the ruler the different distances to the magnetometer for each magnetic field. As you can see, we have different R's, and then we use the formula that we previously mentioned that's linearized with Ln to approximate and get the values on this plot. Here we have our calculations, and with our linearized equation, we can find n, which is negative 2.8262, and k, which is 1.48 times 10 to the negative 6. And using these values, we can find mu by equating the two formulas for the magnetic field of a bar and found 7.4. For the second part of the experiment, we found the off-axis field, where we measured first the on-axis distance, and then we placed the phone in the vertical direction by the same distance and took down each component of the magnetic field at that new location. We found the y component of the field by subtracting the Earth's contribution to the y component to find just the bar magnet's contribution. Now, some observations that we made in the observed model: when the magnetometer was far away from the magnet, it measures a near zero magnetic field in the x direction. But as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So for the computational model, here we have our initial conditions. As you can see, we edited the mu mag from the beginning of the experiment to our value and applied the equation from the principal slide that allows us to find the magnetic field at any point. After that, we created the arrows that represent the magnetic field at different locations of the field with different magnitude and direction. And we also found the electric field at the location that is 45 degrees off the axis. Here we have the results of the magnetic field at 45 degrees at distance d. As you can see, in the x component, we have 6.72 times 10 to the negative 6, and then y component 2.016 times 10 to the negative 5. So some similarities and differences between the models. For the experimental model off-axis field, we got 5.72 times 10 to the negative 5. And then for the computational model off-axis field, we got 2.12 times 10 to the negative 5. For the assumptions that we made, we said the bar magnet acts as a magnetic dipole to apply Biot-Savart law, and we also said that negligible external forces in the computational model. For some possible sources of error, the electronic/magnetic devices in surroundings could have affected the readings, and the location of magnetometer could have been not properly found. Now for some discussion, we have a what if question. What if you haven't oriented your experiment to compensate for magnetic north? This would have changed our results because the Earth's magnetic field would have interfered with bar's magnetic field, making the results less accurate. And what if we were to stick two identical magnets together end to end? That would basically double the magnetic field that is of the magnet, but it will remain in the same direction.